All right, hello everybody. I am EJ Baum working with Eli Vacus on this organic chemistry video. Today we are going to be talking to you guys about ethers and ether synthesis. We are juniors at William & Mary and we are taking organic chemistry 2. And so for our class we are going to be going over, ethers, some of the things about ethers and some reactions. So first, just to start off, what is an ether? An ether is a organic chemistry functional group where there is an alkyl group, and between both the alkyl groups there is an oxygen and another alkyl group. All right. When ether is not an ether is not like something an alkyl group but right next to the double bonded oxygen there is a carbonyl oxygen. This is called an ester and is not an ether. It does not carry the same properties. Another thing that could look like an ether is an anhydride, which has carbonyls on both sides of the double bonded oxygen. And both these things, non-ether is not what we're looking for. And so when we talk about ethers, we're mainly just talking about ROR with just that oxygen in the middle. So what are some of the reactions that go along with ethers? Well, the first one is we start with an alcohol. So we have ROH, and we react it with strong acid. We have H2SO4. You could also use H3PO4, and we use low heat. Now, I want you guys to think about why we would use low heat as opposed to high or mid-heat. There's a reaction that Mary went over when we were going through alcohols. So you pause this video if you need to, but I'm going to keep going. So that reaction, when we have H2SO4 with heat, so let's just pretend we have acid and heat, we undergo an E1 reaction. And so let's say this was butanol. If this was butanol, we would end up with cis and trans-butanol because the carbocation would move after the water pops off. Now, when we have ROH, what happens is we end up, let's just add some carbons in here. This reaction only creates symmetrical ethers, just so you know. This ROH that's in solution is also going to be the attacking nucleophile. And so we're going to have, let's say, let's stick with propanol, even though that's not butanol. And let's put another H on here so we have positive. Just so you know, what happens is this gets attacked by another one of the propanol. Another one of the propanol nucleophiles is lying around, and this doesn't attack H, it attacks this carbon right here, and it performs an SN2 reaction, and the water cleaves off. So what you end up getting is almost an ether. It's almost an ether. It is almost there. It just has this hydrogen atom right here, which is giving it a positive charge. And we have this hydrogen with positive charge. Since our first step in this reaction was protonation, our last step is going to be deprotonation by that conjugate base. So it will be HSO4 minus. I just don't feel like drawing that out right now. It's just for time purposes. And we finally get our ether. Now, naming for ethers is fairly simple. So the common name for this would be dipropyl ether. But the IUPAC name is a little more finicky for symmetrical ethers. It just seems a little unnecessary. This would be propoxypropane. But if you're looking at symmetrical ether, you're probably just going to want to say diethyl ether. In our lab, we say diethyl ether. We don't say ethoxyethane. It just, it's a little redundant. But if, let's say, we want to, make a ether that's not symmetrical. So if we want to make an ether that's not symmetrical, we have to use SN2 reactions, and not in the way we use it here. We have to take another kind of carbon, add an alide. So we have an alkyl halide here, and here we have an alcohol. And so the idea is the alcohol will attack the alkyl halide, and then the halide will take the H, or its conjugate base will take the H. Usually in solution, what we use for the solute, you can get away with, diethyl ether, or usually this is what you're supposed to do, is use the conjugate base for the alcohol, because that conjugate base for the alcohol will easily take that H off. What happens here is this oxygen attacks the R, this gets pushed out, and then we have R1 O R prime, and you still have that positive H lone pair on the bottom. So to get rid of this, you can use Cb or Br negative. There's 4 lone pairs in this Br. Sorry, I didn't do that. Both of them can deprotonate this and finish off your ether. Now, because of this, this is also has a special name. This is called the Williamson ether synthesis. Named after Williamson. This gets you a unsymmetrical ether, so this would be like ethoxy, cyclohexane, or something like that. And so what you want, but when you make this, what you wanted to do, because this is an SN2 reaction occurring, is you want this to be, a primary or a zero-base substituent, and you really want this to be a secondary or tertiary alcohol, just so that, it can attack it and be an SN2 reaction as opposed to SN1. You want to avoid, E2 or E2, E1, any of those, substitution reactions when you're doing this. So make sure this is primary or zero-based, and make sure this is secondary or tertiary.